Two-stage motion problems. So what we're going to do in the next couple of videos is look at just some wrinkles that can be put into these 5 equations of motion questions that you can be prepared for, and then we'll work through those problems. The first one is a two-stage motion problem, 2, 3, 4 stages, it doesn't matter. What's important is that the 5 equations of motion were developed using the idea of a uniform acceleration. That means that if the different parts of the motion, if the acceleration in different parts of the motion changes, then we have to treat those as separate problems. We can't try and use one equation to explain a situation with one acceleration and another acceleration. It won't work. Let's see what that looks like in an example. A car is traveling down the road at 80 kilometers an hour when it needs to stop. The driver has a reaction time of 0.6 seconds. The car can brake at 6.2 meters. That should be meters per second squared. There we go. Determine the stopping distance of the car. So what we're doing here is we've got 2 stages. In stage 1, I'll refer to this as the reaction stage. The acceleration of the car is 0. This is the time from when he realizes that he needs to stop to the time that the stop actually occurs. Starting with an initial velocity of 80 kilometers per hour. This stage is going to last for 0.6 seconds. That's what we mean by reaction time. Is it's going to take the driver 0.6 seconds to realize that he needs to stop and to start applying the brake. Now 80 kilometers an hour is no good. We need it in meters per second. So we're going to divide that by 3.6. We get 22.2 meters per second. And so we can find the displacement that will occur in those 0.6 seconds. Now, you might be thinking that since this is a section of uniform motion, couldn't you use the simplified formula for displacement that we used way back at the beginning of this unit? And the truth is you could. But I find if I always use my 5 equations of motion, whether I need to or not, then if the acceleration is 0, when I substitute that into the equation, then that whole term will go to 0 anyways, and then I get back to my simplified equation. So if I always use the bigger equation, then I won't ever make the mistake of using the simple equation when I should have been using the big equation. So it's just easier to always stick with the big one. So that's the stage 1, and we can see here that it's going to be 13.3 meters before the braking actually begins. Now in stage 2, this is going to be the braking phase. We assume that he's still going at 22.2 meters per second when he starts braking. His acceleration is 6.2 meters per second squared. But we can recognize that that has to be negative 6.2 meters per second squared because he's coming to rest. Since he's coming to rest, or since he's stopping, we can say that the final velocity is 0 as well. Here we're looking for the displacement. So the equation for this one is that 2a displacement is equal to v2 squared minus v1 squared. Substituting the values. Putting my little arrows in everywhere. If I multiply that 2 in, I know I'm coming to rest from 22.2 meters per second. And so 22.2 squared is 492.8. Meters squared per second squared negative divided by negative 12.4 per second squared. So it's going to take 39.7 meters. Okay, so in the first step, so my delta D total is going to be 13.3 meters. And in the second step, my delta D is going to be 39.7 meters, which is going to total to 53 meters. So it's going to take 53 meters for that car to stop. Again, the point here is that if I have two different accelerations, I have to treat those two stages of the motion separately because my equations assume that the acceleration is constant throughout. Another example. A horse pulls a cart from rest to at an acceleration of 5.4 meters per second squared for 5 seconds when the rope attaching the horse and the cart breaks. The crate then slides to rest in another 4 seconds. Determine the total distance traveled by the cart. Okay, so in stage 1, and I'm going to call that the speed up stage. And then I'm going to have stage 2. Don't overthink it, I'll call it the slow down phase. In stage 1, we have an acceleration of 5.4 meters per second squared. From rest, tells me my initial velocity is 0 and a time of 5 seconds before that rope breaks. And I actually need two things here. I need my delta D, and that's important for the question, and I'm going to need my V2 as well. I'm going to need my V2 because I'm going to need it for stage 2. Let me get my delta D and then I'll explain why I need my V2 as well. The equation here is that V1 T plus 1/2 AT squared is my displacement. It is 0 in this term, so I don't have to worry about it. Don't get lazy with units. And that's just calculator work, 67.5 meters. On the other hand, when I go to do stage 2, so I know how far I went in stage 1. In stage 2, I know that my time, it takes me 4 seconds for me to come to rest. To rest in another 4 seconds. But remember way back I said you always need 3 of these variables to find the 4th. And I don't know anything else about this motion. I don't have an acceleration. I can't assume it accelerates at the same rate that it's sped up. It's slowed down. That doesn't make any sense. I don't know the displacement. That's what I'm looking for. And I don't know the speed, the initial speed. But if I think about these two stages and I think about what's happening, you know, here's the horse. I can't draw a horse. I don't know why I'm trying. There's your horse. He's going to speed up to some speed when the rope breaks and then slow down. If this is V2 from stage 1, well, stage 2 occurs immediately after, so it's going to become V1 for stage 2. So what that means then is if I can find the final velocity for stage 1, it will become the initial velocity for stage 2. So let's go ahead and find that using my information here. I'm going to go way down here. A equals V2 minus V1 over t. You've probably noticed that I always try and use information given in the question to solve the problems instead of using stuff that I found later. This just avoids, if I have made a mistake, me carrying that mistake forward to future questions. It isn't necessary. So I'll multiply both sides by 5 seconds here. I get 27 meters per second. That is a fast horse and cart after that time. Not an entirely reasonable value, but that's what the question set up, so let's not worry about that too much. Okay. So what that means is that that becomes V1 for the second stage. So I have V1, V2, T. Now I have 3 things. I can find the 4th thing that I'm interested in. Delta D equals V1 plus V2 divided by 2 times the time. So V1 is 27, V2 is 0 divided by 2 times the time of 4 seconds. And I can just look at the 4 and the 2 canceling out and recognize that's 54 meters. So if I want my total displacement, I have my displacement from stage 1 plus my displacement from stage 2, which is 67.5 plus 54 for a total of, what is that, 121.5? And that is my total displacement for the object through the whole motion. Determine the total displacement traveled by the cart. Yep, so that's the answer right there.